So I'm here today to introduce Dr. Enrico Ramirez-Ruiz. We're very, very excited to have him here. Dr. Ramirez is a professor of astronomy and astrophysics and the Vera Rubin Presidential Chair at the University of California, Santa Cruz, just up Highway 1 from us. He studied at the University of Cambridge, and in 2006, he was selected to be a John Bacall Fellow at the Institute of Advanced Study in Princeton. Since joining the UCSC faculty in 2007, Dr. Ramirez has won a number of awards for his research, including the Packard Fellowship, the NSF Career Award, NSF National Science Foundation, the Radcliffe Fellowship Award at Harvard, the Niels Bohr Professorship from the Danish National Research Foundation, the High Energy Astrophysics Division, aka HEAD Mid-Career Prize for the American Astronomical Society, and the Boucher Award and the Dwight Nicholson Medal from the American Physical Society. That's pretty incredible. He is a fellow of the American Physical Society and a member of the Mexican Academy of Sciences and the American Academy of Arts and Sciences. And this is a part that's really exciting for me. Dr. Ramirez-Ruiz is eager to understand our origins and the disruptive events in the night sky. He works with computer models to understand the cataclysmic death of stars. He recently led efforts to uncover the origin of the heaviest elements in the universe, and he tests his theories with complex computer simulations that defy the boundaries of human experience and the assumptions that we make about the universe. He has co-authored about 280 research papers. 24 of them are in Science and Nature. He has lectured, broadcast, and written widely on science and is a highly decorated teacher and research advisor. Finally, he is a director of the Lamont Institute, and he works vigorously to support the promotion and retention of women and historically marginalized students in STEM. Dr. Ramirez.
Thank you so much for being here. It's been a pleasure being in this institution. I think community colleges are integral to our country, and I'm incredibly delighted to be here and to partner with you. So I'm going to tell you a journey about making gold in the universe. And I want to start with this really beautiful quote by Carl Sagan that says, "The beauty of a living thing is not the atoms that go into it, but the way that those atoms are put together." So I'm hoping to give you like a genealogy tree of every single atom in your body from a cosmological perspective, but I'm actually going to choose a few particular atoms to tell you about how your own history is intimately linked to the history of the universe. So there is actually a really beautiful story to tell of almost every single atom in the periodic table. And so this is just to illustrate that there's many avenues to create these atoms in the universe, and that in fact the creation is intimately linked to the universe. So I'm going to choose a few of the atoms based on our own perspective to take you through that journey. And in particular, I'm going to actually tell you about where you see the emerging neutron stars, and you see these very heavy elements that are orange in the periodic table, that until very recently, we didn't really understand how they were synthesized and made. Yeah? So a lot of the story that I'm going to tell you about is about the origin of those heavy elements. So when we think about ourselves, we are atomically incredibly numerous. This is the number of atoms that you have in your body. 10 to the 28 atoms. So we have more atoms in our body than stars in the universe. That's kind of amazing. The grains of sand in the surface of the Earth. So you're incredibly atomically numerous. And not only that, atoms are incredibly durable. Yeah? So if atoms can speak and tell you the stories, they will tell you about their origins dating back to the Big Bang. Yeah? So I want to ultimately let you, with when you live this space, to think about yourself and the history that you have encoded in your body, and how ultimately you have the history of the universe inside of you. So that's 10 to the 28, a 1 followed by 28 zeros. That's a very large number. And of course, we are certainly very self-centered creatures. So if we think about which is our favorite atom, it has to be oxygen, because oxygen is 65% of our mass. So that's going to be one of the protagonists of our story. Then carbon, hydrogen, and nitrogen. So those 4 atoms can, it basically make up the vast majority of your mass, as humans. And of course, water is an essential component of who we are. But of course, hydrogen is less massive than oxygen. So the vast majority of your mass is actually oxygen. So let's start with hydrogen. So hydrogen is kind of the oldest, cosmologically speaking, atom in the universe. Why? Because it was actually made during the Big Bang. During the first 200 seconds after the Big Bang, there were 2 elements that were made, hydrogen and helium. So the hydrogen of H2O in your body can tell you about the Big Bang. That's when it was made, and it's been this way, since the beginning of the history of the universe. And so, hydrogen and helium are what we call primordial atoms. Those are atoms that were there from the beginning. And astronomers call metals everything that is heavier than helium. So when we talk about the metallicity of the universe, is basically the metal content of the universe after the Big Bang. And in some ways, the degree of metal enrichment in the universe tells you something about its age. If you find a star that is very metal poor, it means that it was made when the universe was very young. And that's because all of these elements are made in the universe, and as a function of time, the metal content of the universe increases. We're constantly producing more and more and more metals, and that means that elements heavier than hydrogen and helium increase as a function of time. Yeah? And if we go back to oxygen, which is our primary component, the story of oxygen is a story that is actually an incredibly beautiful story, because it was not made in the Big Bang. It was synthesized actually in massive stars. So a massive star is a star that is about 10 times the mass of the sun, more or less. Stars that are very, very massive are incredibly luminous. Yeah? So they exhaust their fuel very quickly. I kind of think about them as depending on your culture, you can think about it as the Elvis Presley of humans, or Pedro Infante, which were these very, very luminous individuals, but they had short lives. Yeah? So these stars actually provide the vast majority of the light in the universe come from these very massive stars. And they fight their battle against gravity. Gravity wants to contract them, because gravity is an attracting force, by basically fusing elements in their cores. Yeah? And massive stars basically fuse elements all the way to iron, because iron is the most stable nuclei in the universe. And after iron, gravity has won. There's no more nuclear reactions that can actually give you heat, and the core of the star collapses. And in that collapse, an object in the center is formed, a neutron star. So as the material increases in density, it reaches to nuclear densities, and they make a neutron star. And in that process, they produce a very large explosion, which is called a supernova explosion. And it is in that supernova explosion that oxygen is actually synthesized. So as we talked about, I worked a lot on computer simulation. So what you're seeing here is time as a function of time, as a function there, the clock. You're seeing the core of these very massive stars collapsing. And what you're seeing is entropy, so temperature. The temperature is increasing, material is falling. It's almost like a pressure cooker. The pressure is basically ultimately increasing, and is actually able to overturn the collapse and sends a shock wave. And it is in that shock wave where oxygen is actually made. And as you see, the collapse of this core and the formation of this neutron star, which is going to be a central protagonist of our story, lasts a fraction of a second. and it launches these explosions, yeah, that are some of the brightest explosions in the universe. So I see there a supernova explosion before and after in a galaxy nearby. That supernova explosion puts light, a combined amount of light compared to the entire galaxy. And a galaxy has 10 to the 11 stars, 100 billion stars. And one dead of one massive star illuminates the universe and can actually compete with the entire luminosity of a galaxy. Yeah? And it is that trigger that makes oxygen in the universe. So if we go close to home, this is one of our nearby supernova explosions. This supernova explosion is about 10,000 years old. And what you see there glowing in blue are freshly synthesized oxygen atoms. So the atoms that are in your body once were synthesized in those explosions. And then if you ask how many supernova explosions have taken to make my oxygen or oxygen together, it's about hundreds of millions of supernovae. Over the history of the universe created oxygen, that oxygen mixed and gave ultimately rise to our solar system. Yeah? So the genealogy tree of your oxygen goes back hundreds of millions of generations of supernova explosions. Now, this is basically a computer simulation of a galaxy like our own. And these supernova are happening in the plane of the galaxy and are actually, because they're injecting so much energy, are creating these winds. So metals are basically very efficiently being mixed within a galaxy. So we know for a fact that oxygen in your body have actually, the atoms themselves have traversed the entire Milky Way back and forth, which is kind of amazing, ultimately to lead to our own solar system. So our galaxy is an incredibly dynamical entity, and this oxygen recycling has been going on for millions, if not hundreds of millions of years. Now, if you want to go closer to home, we can think about all of these oxygen atoms were mixed in the Milky Way. They ultimately came together into a cloud there. The cloud ultimately collapsed and gave rise to our solar system. Yeah? And as a function of time, as we create more and more solar systems, the metal content of the clouds increase. And what we know for a fact is that if the cloud doesn't have a lot of metals, you cannot produce planets. So planetary formation also requires a significant amount of metals, and it's something that has just happened very recently in the history of our universe. Yeah? So life, at least from a planetary perspective, is something relatively young in our own universe. Now, what I really love about the story of oxygen recycling is that it continues all the way to today. So each of us goes to about 180 liters of oxygen every day just by breathing. I'm incredibly grateful to be here, not only because I get to share my story with you, because I'm also stealing your oxygen atoms. And when I go home, I'm going to take a lot of your history with me. Yeah? So we are constantly recycling our oxygen atoms. And because the atmosphere of the Earth doesn't really lose a lot of oxygen, you can think about, well, what about previous generations of humans? Do I carry any of their atoms? The answer is yes. So for example, in your body, you have about 10 to the 5, 100,000 atoms that once belonged to Frida Kahlo. Remember, atomically, you're incredibly numerous. Yeah? So if for some reason you feel uninspired or not creative, you have to reach deep inside you to find those atoms. Yeah? And you can do that for, the entire humanity. So I have here some of my heroes, which you may or may not recognize, but you have Celia Cruz. You have to recognize him, of course. Frida Octavio Paz, which is a Nobel Prize writer from Mexico, and Sor Juana Inés de la Cruz, also a writer from Mexico. So I can count my atoms. Now there's individuals whose atoms we really don't count in our body, so forget about those. But that just tells you about the amazing constant recycle that is happening in an atmosphere, and the fact that we are recycling constantly so many oxygen atoms in our body. So we are not only cosmic recycle, but also human recycling. Yeah? And there's so much more that unite us than divide us when you think about sharing our oxygen atoms. You know, atomically, we're so much more similar to each other, and we have the same genealogy tree. So the story that I wanted to tell you about is the story of how these very heavy elements form. And by heavy elements, I picked here a few of my favorite, and you know why. Uranium and thorium, which are radioactive elements, which are actually essential to life. I'm going to convince you that those two elements are essential to us being here. And gold, you know, just because who doesn't like gold? Gold is the most noble of all metals, and we didn't really understand, or you know, for a long period of time, where these elements came from. And at the end of my talk, I'll tell you about why thorium and uranium are actually essential to life. Yeah. And I know that with the students we talked a little about astrobiology. So here are some implications about element formation into life. So gold is the most noble of all metals. So I'm going to center the story of these heavy elements in gold. Is the most noble of all heavy elements. So that means that it's the least interactive. So it's not corrosive, you know, and that's why gold always keeps its shine. Yeah. We have about 10 to the 18 atoms of gold in our body. That's kind of amazing. And if you like sushi, your gold content actually increases because fish retains a lot of heavy elements. So I'm going to tell you about a unit that it's actually quite important, which is called 1 part per billion. That's more or less the gold content in the universe. And just to give you kind of an intuition of what it is, if you take an Olympic pool that has about 600,000 gallons, and you take a teaspoon in that pool, that's about 1 part per billion. So if you think about the universe being a pool, and you think about a teaspoon, that's the amount of gold that we have in the universe, proportionally compared to all the mass in the universe. So more specifically here, I'd give you a table. No? So the universe has 0.6 parts per billion of gold. The sun has about 1 part per billion. If you ever hear that we should go and mine meteorites, is because they have a very large proportion of these heavy elements. You know, they have 100 times more gold per unit mass than you know, the universe. Interestingly, the vast majority right now of gold that it's not being mined is in the ocean, but it's actually in small quantities. And thankfully, we haven't found a way to mine the ocean for gold in a way that, you know, doesn't create any pollution. But then if you, again, don't think about your own shininess, you should actually think that you're 50 times more rich in gold than the universe. Yeah? That's kind of amazing. So if you're feeling like it's not your day, just think about those enhancement of gold in your body. And of course, when we think about an origin story of gold, you know, I go back to my ancestors, and my ancestors used to think that gold was the sweat of the sun that basically fell in these large pieces in the surface of the earth. And they were not quite right, but they were not quite wrong, because as we saw, the sun has a significant amount of gold, but it was not formed inside the sun. So what I'm going to tell you about is the history of actually how to make gold. And therefore, the title of the talk is Alchemy. No, because as humans, we've been obsessed with trying to make gold, and I'm going to tell you that it's actually not an easy task to make gold, and even the universe struggles making gold. So when I was a grad student, we started thinking about a gold recipe. And the gold recipe involves 2 neutron stars, the densest objects in the universe, merging together at billions of degrees temperatures, and ultimately forming a black hole. And we think that's the way that you can make gold. So gold requires the most extreme temperatures in the universe and the most extreme densities in the universe. And this was basically what it was postulated. And what I'm going to tell you about is whether or not we were right. So I'm going to give you a little bit of more insight about a neutron star. So the neutron star was that leftover central object after a massive star collapse. And they're the densest objects in the universe. They have the mass of the sun, but the radius here, here is Manhattan, but you can think about the San Francisco Bay. Yeah? So 10-mile radius and the mass of the sun. So the density is 14 orders of magnitude higher than the density of water. So if I'm in the surface of a neutron star and I want to escape its gravity, I have to move at 30% of the speed of light in order to actually leave that body. And the recipe says, oh, you don't only need 1, but you need 2. And this is not unusual because massive stars don't like to live their lives by themselves. The vast majority of massive stars have a companion, and about 2% of neutron stars belong to a binary system. So having a companion is actually something common, and I'm going to tell you about what happens when you have 2 neutron stars orbiting around each other. So when this happens, and we were talking this afternoon about this, Einstein tells you that the motion of matter creates these waves, these gravitational waves, these distortions of space and time. And as these 2 objects are orbiting each other, they create these high amplitude waves, and those waves carry both energy and angular momentum. So that means that the system starts coming together slowly. And that dance, that beautiful dance, lasts hundreds of millions of years until the 2 objects basically come together. And it is at that specific point in time where you get higher temperatures, higher densities, where we actually think that gold is produced. Okay? It sounds like science fiction. In our own Milky Way, we know of about 20 objects that are 2 neutron stars. Yeah? And in fact, we tested the theory of relativity by understanding how they're actually, the rate at which they're coming together. And basically making a prediction that in fact, Einstein's prediction of the loss of angular momentum and energy through gravitational waves was correct. And that gave the Nobel Prize to Pauls and Taylor. I'm going to show you a simulation, one of the simulations that I did for my PhD. The 2 neutron stars are coming together, and what you're seeing is temperature. They touch each other. They create huge amounts of temperature, huge temperatures in that interface. Enough temperatures that you can actually create the right conditions. And, oops. I was trying to point. Oh, there you go. So what you're going to see as these 2 objects are orbiting each other, they're going to eject some mass in what we call the outer Lagrangian points, which is 2 mathematical points. And this material that is basically ejected out from the system, which we call the tidal tails, is where we actually think the gold is actually created. All of these heavy elements are synthesized in these tails. And then the central object ultimately is going to collapse into a black hole. So the question was, how can we test this theory? And the prediction that we made was that when these tails are basically ejected and are producing heavy elements, these heavy elements are radioactive. And as they decay, they heat up the material. And we expect to, we expect, for example, an optical transient to last about a week. Now, this was at a time in which our ability to detect gravitational waves was increasing. We actually thought, oh, we're going to actually see two objects merge through gravitational waves. And then if we go and point out an optical telescope, we should see a transient associated with that gravitational wave system. And the properties of the transient will ultimately tell us whether or not these heavy elements were made. And this is exactly what we saw on August 17, 2017, which after the birth of my two kids is one of my favorite days. Yeah. Why? So what we saw here, this is frequency of the gravitational waves as a function of time. This detector on Earth was ultimately able to measure the gravitational wave signal. These objects are coming together, so that means that they're increasing the frequency until they merge. Okay? So we got a signal. We detected a gravitational wave coming from two neutron stars. And then the way that gravitational wave detectors work are very similar to how your ears work. Yeah? And in the US, we have two gravitational wave detectors, one northwest and one southeast. So when a gravitational wave goes by, it actually moves the detector in both of those places. But for example, if you have two, well, we have two ears. if you actually think about trying to determine where a sound comes from and you close your eyes, you're completely unable to hear a sound or where it comes from in the plane of symmetry between your two ears. You wouldn't know if it's coming from the front or from the back. So with two detectors, that's exactly what, the uncertainties that we have in the sky. We say, well, the gravitational wave came from some plane. Yeah? So these are black hole mergers, but then this is the neutron star merger. And then you say, oh, but you were able to determine with much higher precision where in the sky this event actually happened. And the reason why is because one day before this event arrived to Earth, we turned on a third detector in Italy. So we had three detectors. So if you had 3 ears, you'll be able to point the sound much more effectively. I mean, imagine the coincidence of that. We were incredibly lucky that the brightest gravitational wave source arrived to Earth a day after we turned on the third detector. So we were able to get position uncertainty in the sky. And thank you. And what ended up happening is everyone in the field of astronomy went to look for the electromagnetic signature of this event. It says, okay, now we saw these two objects, what sort of light they produce. So at Santa Cruz, we are members, and we're not very inventive as astronomers. Our name is the 1 meter 2 hemisphere telescopes. Why? Because we have a 1 meter telescope in Lick Observatory, and we have a 1 meter telescope that we rented in Chile, the SWOBE telescope. Why? Because we didn't know if the event was going to happen in the north or in the south. Yeah? The universe doesn't care about north and south. So we had two telescopes, and we were basically desperate to find the electromagnetic signature. And I'm going to give you a little bit of a story about our competitors. So we were competing with Harvard and Chicago, primarily, that have the Blanco 4 meter telescope. So they have 16 times the light collecting power and 12 times the field of view. So they had better equipment than we do. We only had a 1 meter telescope. So we had to be clever in order to be able to outsmart them. And I kind of think about our story as the David and Goliath story, in which ultimately we did outsmart the status quo universities. And a public university actually detected the transient first. So this is what we did. So this is the position in the sky of where we know the event took place. You can see it's in the south. Chile, at the time this was detected, actually was daytime. So we still had to wait until it became it became dark to actually look for this transient. In fact, if there would have been anyone in Africa looking for this, they probably would have detected before us. Now, we had two choices. One choice, this is basically the entire field of view. Now, the gravitational wave signal gives you the distance. You can actually measure the distance of the object. So if you have an uncertainty in the sky, you can think of it as a volume. And we know all the galaxies in that volume because we have surveyed them. We survey the universe, and we know every single one of those. So one technique is take the entire sky and start basically tiling the sky, looking for a transient. But of course, we were going to lose if we did that because the other teams had better telescopes, more field of view, they can actually look. But we say, well, what about, rather than look at the entire sky, we're just going to look at where the galaxies are and just target the galaxies. Yeah? So David Coulter, a grad student at UC Santa Cruz, derived an algorithm that actually said, I'm going to basically maximize every pointing of the telescope to get as many galaxies as possible every time I look. And we did that. So this is the story. 8:14 p.m., 46 minutes after sunset. For those astronomers in the room, it's not easy to observe soon after sunset. 10 hours and 33 minutes after the trigger. So that's, if you would have had a telescope in Africa, you would have detected the transient. And these are our pointings. In a matter of less than half an hour, we were able to uncover the gravitational wave emission coming from this galaxy. And we beat the other teams by a minute. So the glory was just a minute. Now, one of the predictions that we have made is that if this transient produced a lot of heavy elements, the transient was going to look very red. And that's exactly what we saw. It started very blue, but then it became incredibly red. And the spectrum actually was consistent with the opacity, the level of absorption that we expected from heavy elements. Giving credence that we did, in fact, detect the formation of heavy elements during this process. And as you saw, we used the SWAP telescope in Chile, who was the first one to detect, a 1-meter telescope. So this is our team at UC Santa Cruz. I'm proud to be the oldest member of the team. We have an incredibly vibrant early career team. Dave Coulter was the individual that developed the software to ultimately outsmart the other collaboration. The collaboration is led by my colleague Ryan Foley. I am a theorist, he's an observer. This is Cesar, who's from Costa Rica, Ariadna, who's from Mexico, and Charlie Kilpatrick was the first one actually to see the transient in real time by looking at image difference and say, I think we found it. So it was an incredibly exciting time. And in addition, we could tell within the astronomical community, but we cannot disseminate this only after 6 months. No? And we had to write the papers all in secrecy in advance of the press release. So this is the paper from the theoretical perspective in Nature, where we say the origin of heavy elements in binary neutron star mergers from a gravitational wave event, showing fairly convincingly that the models that we have made in anticipation of this of the detection match the observations very well. So how much gold this event produced? About a Jupiter mass of gold. No? That's amazing. I mean, Jupiter has of the order of 10 to the 30 grams. A gram of gold is about $10. So 10 to the $31, that's a lot of money. If this is not impressive enough, a Jupiter mass of gold is equivalent to the gold content of about 1 million stars. So one event supplies with a lot of gold. So and it kind of makes sense because you have to produce one neutron star, you have to produce another neutron star, and you have to wait for them to merge. So that's a rare event, but the production, the amount of mass that you produce is actually very large. And in fact, this theory is really beautifully validated by observations of low metallicity stars. So imagine that you are in the early universe. There's not a lot of metals, and you get one of these events that produces that much mass. And I like to think about chemical evolution. Imagine that gold is chocolate, and imagine that you have a process that produces little amount of chocolate, but very often you can think of a chocolate cookie with a very thin layer of chocolate. Yeah, so there's not enough variations, but these objects are more like chocolate chip cookies because you produce all the chocolate localized. So if you make stars close to the chocolate chip cookie, you will have a lot of gold, and if you made it away from the chocolate cookie, you have little gold, and that's what we see. We see that the variations from star to star in terms of their gold content is very large. So these events, have been operating since the early universe, and they have led to large variations of gold between stars. And we published 4 articles in Science, and this was deemed the breakthrough of the year. And as a team, we're incredibly proud that every single one of our papers were actually led by an early career scientist. So when you think about the gold content in your body, the way that you should think about this is that over the history of the Milky Way, there's been many, many events that have actually ultimately mixed to give rise to the cloud where we ultimately were made of. Yeah? And if you calculate, there's about 100,000 to 10,000 neutron star merger events in your body that produce the gold that you currently have. Yeah, that have been constantly mixed in the interstellar medium. So I'm going to tell you, the elements that we saw in this neutron star merger, as you see here, are all the orange elements. And I'm going to tell you about these 2 elements, thorium and uranium, which are incredibly important for life. And they're also produced in these neutron star mergers. Why are these elements essential to life? Because the vast majority of the heating of the core of the Earth, so this is our planet. Oops. The core of the Earth is being heated by uranium and thorium. Those are radioactive elements that are providing most of the heat in the core. They lead to these fluid motions, and those fluid motions lead to the creation of a magnetic field. Yeah? And you know how important, maybe you don't, but having a magnetic field on Earth is essential to life. Why? Because it shields us from very high energy particles trying to come to Earth. So it protects us. It's like our shield. So what we think is that the level of uranium and thorium determines whether or not the Earth can have a magnetic field, and that's ultimately linked to neutron star mergers. And what we see, remember we talked about the chocolate chip cookie? Well, those variations in stars get smooth as a function of time because you're mixing more and more metals. But in today's universe, we can find 2 stars identical to the sun, but they have changes in uranium and thorium by a factor of 3. So for example, we think that if you have a lot of radiogenic heating, the fluid motions are so vigorous and intense that you can actually not make a magnetic field. So we think that some stars that are rich in these elements will not be able to produce a magnetic field, and therefore the Earth will be inhabitable. It seems like the Earth has the right amount of precious elements, and if you had less, you likely make a magnetic field, but you won't have any volcanism. And volcanism is also incredibly important for us to basically create an atmosphere with metals. Yeah? So this is ultimately that even though these elements are a very small fraction of the total mass of the universe, they are essential to life, and they are ultimately providing the vast majority of the heating of the core of the Earth. So we talked about we want to center the story in us. We want to center the story on the gold that we have, on the gold that the Earth has, and the heavy elements, which are essential to life. But I want to tell you, I just want to finish my talk telling you about what about gold in the surface of the Earth? Yeah? And this was for a long time a geological problem. Why? Because when the Earth was actually made, it was incredibly hot. It was molten. And what happened to all the heavy elements? They sank into the center. And then the Earth cooled and didn't have a lot of blink in the surface. So the question is, where is all the gold in the surface of the Earth came from? And ultimately, another important thing to know is that gold actually gets highly concentrated in high pressure environments. So, if you have these high pressure environments and material goes through the surface from high pressure, then that's where you can actually find a lot of high concentration of gold. And that's why we have mines very close to these high pressure points. But people actually say, well, what about all of the gold that it's in the surface? Where it come from? All the gold should be in the core. And the answer is actually in the late bombardment. Remember that meteorites have this excess level of gold. In the late bombardment, this is at the time that the moon was formed. The moon was actually formed at a really massive collision between two objects. And at that same time, when the moon was getting all those craters, all of these meteorites were basically painting the surface of the Earth with gold. So the vast majority of the gold that we have in the surface of the Earth came from basically all of those impacts. And that leads me both thinking about the recycling of our atoms in this room, the recycling of atoms in the universe, brings me to this story. So my grandfather, who was a member of indigenous culture in Mexico called the Chichimecas, told me this myth. And it said, very similar to gold coming to the surface of the Earth, your essence, when you're actually created, comes rushing to reach you. But in its way, it actually fragments into millions of pieces. It says, when you're going to gain consciousness, you're going to feel incomplete because you're missing your pieces. But the story was like, but this is really an opportunity for you, because it's not that those pieces got shattered and scattered all over the floor, they fell into other people. And only by sharing those pieces with other people, you will become more complete. So you're going to have people in your life that are going to have these immense pieces that are going to make you whole. But in your quest of being complete, every single piece is essential. So you should treat everyone with respect and care. And every single individual has something to teach you. Not only that, every single individual shares your same atoms. Particularly once you leave this room, imagine all the plethora of experiences and exciting things that you will carry with you and memories. And I hope ultimately that I convince you that the journey of our atoms in our body is an incredibly interesting story, that the universe have produced the vast majority of heavy elements in the periodic table after the Big Bang, and they were basically continuously being made. And ultimately, that UC Santa Cruz was the team that first detected the electromagnetic wave signatures coming off from neutron star mergers, confirming that these really exotic objects are really the culprits to make gold in the universe and these heavy elements. And I'll stop there and thank you.
Thank you, Dr. Ramirez. Keep the applause going. We have a chance to ask questions. Anything that you want to ask. So I see a couple hands back there. I'll make my way back there, and I will go anywhere in the room where there is a question. So.
Hi, Professor. Thanks a lot. I appreciate the opportunity to have you come here. Someone to ask you. There's billions of galaxies in the universe. So knowing physics as well as you do, I'm pretty sure that the conditions, the physics in this galaxy are very, very similar to the physics in another galaxy. I've been told that if my thumbnail was the size of a galaxy, then the universe would be the size of Dodger Stadium. So that's generally true. So if that's the case, and the conditions which create amino acids must exist everywhere, how crazy do you think it is that life can form throughout the universe? Thank you.
Yeah, not crazy at all. No, I think in general when we think about the existence of life, I mean we think it from a very from our own perspective of how life came to be on Earth, and how biology chose the pathways, the biological and chemical pathways to give rise to us, in general. So Frank Drake, which was a colleague of mine at UC Santa Cruz, came up with a very famous equation which is called the Drake equation. And he was thinking about, well, let's think about the conditions of life. So you rightly pointed out, in our own Milky Way, there's about hundreds of billions of stars, maybe tens of billions that are similar to our own sun. And then they say, well, we need an Earth-like planet at a distance in which liquid water can exist. And in fact, that's actually a fairly common occurrence. Yeah, so there's actually probably 1 billion stars in our own galaxy that we have an Earth-like planet where water can exist in liquid form. So that's already 2 really important conditions that seem to be fairly likely in the universe, no? And then you start thinking about all the other attributes that you need to. And then, of course, you start thinking about, can we communicate with those or not? And how long have we been a technologically advanced society compared to the age of the Earth, which is a very small fraction of the time. So the answer is yes. Now, what it's interesting is when we think about galaxies, not every single galaxy is the same. So galaxies like the Milky Way seem to be galaxies that are, fairly metal rich. If you have galaxies that are smaller, they don't have as many metals, so we don't think that planets would have formed there. But I agree with your intuition that the universe is so vast, the conditions of life are not that drastically unique, and that it's likely that life would have actually formed similarly with similar pathways to the ones that we know. I mean, the question that I'm always asked is like, but can we just go to other planets and destroy the one we have? And the answer is no. I mean, like if you think about how long it will take us to even get to the nearest star, this idea that we're just gonna not take care of our own Earth and be able to go to another planet, that's the one that worries me, so I feel like ultimately we have to really take care of our Earth and really, be introspective about how we're living today to make sure that we leave, enough resources for generations to come. But yeah, I agree with you that. And right now, people are incredibly excited to actually think about signatures of life in other planets, nearby planets. We currently have about 10 Earth-like planets relatively nearby where we actually can take a transmission spectra. That means that the light from the star going through the atmosphere of the planet can lead to some signatures that we can see. Is there oxygen there? Do we think that the oxygen that is there is made by photosynthesis, or is there any other chemical processes? So I think my feeling is that the next big discovery in astronomy is going to be the signatures of life in the atmosphere of other planets. And by life, I mean plants, probably.
Hello.
Hi.
So how did the gold originate in Earth, and why was gold in certain parts of the Earth and in parts of the world, like in the early 20th century when a few lucky people discovered gold during the California gold rush?
Yeah, so the question that you ask is an incredibly insightful question, because you should have challenged me pretty significantly what I told you that gold is. Okay, wait a second. For generations, we have actually discovered these gold nuggets, and they're higher concentrations than 1 part in a billion. And the answer is, as we were talking about, that gold is actually concentrated in these high density pressure flows in the mantle of the Earth, and then it's basically brought up to, so for example, if you look at mines, where mines are in particular places on Earth where these kind of high concentration flows are coming to the surface of the Earth, and gold is basically found in high concentrations. And what it's relatively sad about humans today is that the vast majority of the gold in mines has already been mined. So the gold nuggets that we find that were highly concentrated by us by the Earth's mantle high pressure processes, all of this have basically been mined. And the vast majority of gold that it is in the surface is now no longer in high concentration. And not only that, 80% of all the gold that has ever been mined, is stored someplace. Not surprising, it's an accumulation of wealth. Gold has not many uses because, as I was saying, it's not very, reactive metal. I don't know if that answers your question, that in some ways, gold was not just uniformly spread, through these impacts, but it was actually highly concentrated, distributed. And that's why people were able to actually know exactly where to look for gold, because they looked at mines and they looked, deep into, as close as they can get through these high concentration flows to look for gold. But the vast majority of those mines have already been extracted, the gold there. Does that make sense? Yeah.
Are there any other questions? Yes. Yay. Okay, please.
Yeah, thanks, Professor. So many interesting ideas. You mentioned that the concentration of metal in the universe is increasing, and we're sort of got formed in a sweet spot for life to form. That leads me to ask, well, if it keeps increasing, is the universe going to end in a giant metal crystal, or is there going to be a hydrogen shortage?
Yeah, so sadly, the production rate in the universe is going to drastically decrease. So as you probably have heard, the universe is expanding. So everything is coming apart. So what's going to happen is that the density of gas is actually going to decrease. And at some point, we're not going to be able to form stars anymore. So the fate of the universe, as we extrapolate, is a pretty bleak fate, because it means that no stars will be formed, no more metals will be formed, and there will be no light in the universe. As soon as fusion will stop, everything will become incredibly dark. And if you think about, that's going to take a long time. But yeah, that's kind of the long-term perspective of the universe. That is really the expansion that is going to actually drive the fact that we're not going to be able to form, new stars. Now, next generations are going to have an incredible sky to look at, because as you know, the Andromeda Galaxy, which is our nearest galaxy, is coming towards us, and we're going to collide with the Andromeda Galaxy. So the night sky in about 5 billion years from now, just as the sun is basically stopped burning hydrogen, is actually going to look fantastic, no? And then we're going to merge with that galaxy, but then ultimately, as we expand, the horizon is going to become darker and darker, and there's not going to be, no longer stars in the horizon, and everything is going to be dark and cold. But yes, and no more metals will be produced. So maybe we will be a cold solid, but no more new metals. Yeah.
Okay, I have one over here, Herbert.
Hello, my name is Izu, and I'm in 5th grade. And when you said the neutron star binary, that when they merge, they produce gold, and they turn into a black hole, won't the black hole suck up the tidal forces? The tidal waves?
Yeah, incredibly thoughtful question. So what ends up happening, when these two objects come together, there's a little bit of mass, like about 1% of a solar mass of material, that it's able to escape the gravitational field of these two objects merging. Yeah? It's, for example, when you send a rocket from the surface of the Earth, you need to send it to some high velocity in order for the gravity of the Earth not to pull it back. So the tidal tails are able to basically be thrown out. Now, when black holes accrete material, we sometimes think of black holes as a vacuum cleaner. And in reality, nothing happens to the gravity. Just the gravity is highly concentrated. But as material basically falls in, it also gets heat up. So actually, black holes, material as it falls into black holes, also ejects winds. So there's some material before you get to the region where there's no more escape that actually ejects material. So there are opportunities around black holes to throw material that is not sucked in, but a significant fraction of the mass will ultimately end into the black hole. And you're right, the black hole will basically ultimately grow. So a lot of the gold that was made in that movie will ultimately fall into the black hole and will be gone. But a fraction of it will be able to escape. You can talk to your gold atoms and see if they can tell you the story about how they were able to escape the gravity of a black hole. But yeah, that's really insightful question. Yeah.
Okay, this tells you something else. My name is Ruth Alota. I'm a retired teacher, but I took a course in college way back at Sonoma State on cosmology and extraterrestrial intelligence. I've always been fascinated by it, and the concept of the black hole really got to me because I heard that once something goes into the black hole, it can't get out. And so could you answer that question? And also about volcanism? I wasn't comprehending that part.
Yeah, I'll answer the second one, which is much easier to answer than the first one. So a lot of what creates volcanism in the mantle of the Earth comes from the interior heat, no? So planets are heated up by radioactive decay. And it's, ultimately today, initially there were other elements, but today the elements that have a half-life that are able to heat up the interior of the Earth are these uranium and thorium. So if you were to decrease the content, the heating rate will decrease, and then the motions in the outer parts of the Earth will decrease. And then you will not have, like a pressure cooker, enough pressure to actually make volcanism take place in the surface of the Earth. And of course, volcanism is really important for the chemistry of our atmosphere. The second part is an incredibly interesting part, which I can tell you whatever I want, but know that I'm wrong, because we don't understand what happens when material falls into a black hole. So we can describe a black hole very well until what we call the event horizon, which is the region at which the escape velocity is close to the speed of light. And inside that, we know that the gravitational field is very strong, but we know that it cannot communicate with us. Because if light cannot escape, how are we going to communicate? And a lot of the laws of physics break down in that interface, and there's a lot of work trying to understand it, but we are far from understanding what happens when material falls into the black hole. What I can tell you is that we know that black holes grow. As material falls in, that increases their masses, and they basically grow and get bigger. So certainly energy and mass is conserved as this happens, but really what happens inside the black hole is something that we don't understand.
Hi, Princess Gilbert, biology professor. I had a question about gold and its use on space shuttles. You mentioned it's not very reactive, and so I was wondering if you knew why we put it on things going to space. Like, is that, yeah.
Yeah, I actually don't know of many technological applications of gold for electronics or other things. I also don't know if, I've been trying to, maybe you can help me. I've been trying to look for biological applications of gold, in a biological process. And of course, because it's not very reactive, it doesn't seem that it's an agent of many things. I think if you look for, platinum, which is also a heavy element, which is also one of my favorite, that one is much more effective because it's highly conductive. So I'm not aware of many electronics that use any gold. I wonder if it could in principle be used to actually try to measure the cosmic ray irradiation impacting into gold. That could be, because it may be fairly resistant to it, so maybe there's a way of calculating their interaction with cosmic radiation, but I'll look it up, but I haven't heard of many applications of gold. I mean, the Aztecs and other cultures love gold in the sense because if you were buried with it, it will carry its essence forever because it did not decay. And that's why the vast majority of gold today is just in a vault. And it has price because we've given them price and we give them value. But in terms of technologically speaking, I'm not entirely sure that it does. But I could be completely wrong, but I'll look it up.
So I'm looking for a hand. I see Lauren Steck. By the way, thank you for coming. Trustee Steck. Lauren is with our Board of Trustees at MPC.
Sure, put me on the spot now. I have to ask an intelligent question, yeah. So if I understand it correctly, neutron stars are spinning around one another. They're going faster, getting closer, faster and faster, and at some point, I imagine it's something like a centripetal force that'll tear pieces off, and those are the
And the
things-
tidal force, as we heard.
Yes. So, but they'll tear these pieces off, and that is the area in which gold, as we know it, will form. I'm wondering about the timeline for that. Is this a tail that gets torn off, or is it a discrete? Is it a millisecond that these things that the tail gets torn off before the neutron stars collapse into a black hole? Is it a short time, or is it a long time? Or these things, in the illustration, it's almost like they were round, a volume that's round. But is it a tail that extends a long ways?
Yeah, there are two tidal tails. So the way that you think about it, kind of mathematically, to answer that insightful question about why the material comes out, is because the material is basically collapsing, no? So material finds itself outside of the potential as the potential moves in, so it finds itself at higher velocity than the local escape velocity. And the two edges are called the two Lagrangian points, and the Lagrangian points move inwards, and then material basically it's thrown out. And what you get is these tidal tail features that are fairly, tidally tail, and then basically expand and move at about 0.3 of the speed of light. And then they basically interact with interstellar medium, expand, and ultimately become round. But initially, they're very asymmetric. So you saw it in the movie. It just took like tens of milliseconds by the time they get out. Now, of course, it takes about a week. You saw for these tails to expand, sort of the radiation is allowed to escape from these expanding tails. But they're also highly asymmetric. So there are things about like, do we see polarization of light because they're not completely spherically symmetric? Can we basically tell the asymmetry from the radiation?
I'm going to ask one more question on behalf of our STEM students. If after this STEM talk, I've decided I want to do what you do, how do I get there?
Yeah, that's an excellent question. So if you want to be an astrophysicist, I would say, I think the life story of an astronomer is you're first a physicist. You study a physics degree. Today, it seems like understanding coding is an essential component not only of physics, but almost every STEM degree. So I encourage you to learn Python. Python seems to be the universal language of coding. And then, seek for opportunities to do research. In my own life, I was really lucky to have the opportunity to do what it's called a research experience for undergraduates. When I was in Mexico, and I came to Los Alamos National Laboratory, and that changed my life. Had an amazing mentor. So getting opportunities to do research, it doesn't matter how early career you are, the opportunities are. If you're interested in astronomy in general, I run a program that it's called the LAMAT program, that it's to support students doing internships. Contact me, send me an email. I'm easy to find. If you look at UC Santa Cruz Department of Astronomy, and you look at the only Latino in the list, that's me. And I think, never listen to anyone that tells you that you're not good enough to do math, because everyone is incredibly apt to do math, and it's just that you haven't had effective teachers. Follow your passion, and if you need some barriers being removed along the way, contact me or some of your amazing teachers to help you pave the way so that you can follow your dream. So
Thank you, Dr. Ramirez. And thank you, MPC, for joining us tonight. We hope that we will be having 2 or 3 STEM talks next year, so watch out for the posters and announcements. And we're very excited that we had you here, so thank you once
so much
again.
for having me.
So before we let Dr. Enrico go, our math club president, Dave, would like to come forward and not only share his atoms, but also tell you that you're now part of the Lobo family. And so we want to give you a MPC bag with some swag. So hopefully at UC Santa Cruz, you feel proud to be a Lobo. And more importantly, we want to give you the emblem logo of the math club with the math club students that participated in your talk today.
Thank
So
you.